We are at the end of Module 9, excuse me, and we are covering pages 303 through 308 today. We've been talking about polar bonds. Today we're going to talk about whether molecules are polar. A polar bond is when one side of it is more negative and one side is more positive. So just like that, a polar molecule is going to be a molecule. You have to visualize the shape of it that has one side of it being more positive and one side of it being more negative, but the overall molecule, not just the bonds within the molecule. Okay, here are some rules. When is a molecule polar covalent? And for short, we can just call it polar. Number 1, the molecule must have polar bonds. Okay, so first of all, remember that means that the molecule must be covalent. It's not an ionic compound, which is a nonmetal and a metal together. We're talking about a covalent compound with two nonmetals. Secondly, the polar bonds cannot be of equal strength and pull in opposite directions. This would essentially cancel the two out, canceling each other out. And we'll see what I mean when we get into the geometries of that. Okay? The polar bonds cannot be of equal strength and pull in opposite directions. Let's take an example here real quick. CO2. Okay? After you figure out the Lewis structure, you would see that this is a molecule that has double bonds. The carbon is in the middle, and then the oxygen has two other lone pairs, each oxygen does. So the geometry of this would be a linear shape. Okay, so is this molecule polar? Does it have one side that is more negative and one side that is more positive? Well, let's look at these rules. The molecule must have polar bonds. Yes, these bonds are polar. If you want to label them, we point the arrow toward the oxygen because the oxygen is more electronegative. So the more negative charge is going to be at the outsides of the molecule, at the oxygen, and the more positive charge is going to be on the inside, the carbon, because the carbon is usually missing electrons, therefore has more protons, giving it a more positive charge overall. But number 2 says the polar bonds cannot be of equal strength and pull in opposite directions. These bonds are all of equal strength because they're all the same type of bond. They're all from a carbon to an oxygen. So they're all of equal strength and they pull in directly opposite directions. So this molecule cannot be polar. Now, another way to think of it is if you have, let's say this is our carbon, this is our linear shape right here. The carbon is in the center, the oxygens are at the outside. Is there a way that you could draw a line through this molecule somehow to show that one side of it is positive and one side of it is negative? No, there's not. Because if you draw a line through the center, you still have the negatives here. If you draw a line through this way, you still have the negatives on the outside here. Okay, so you have to be able to see the positive side of the molecule and the negative side. But here the positive is stuck right in the middle, surrounded by these two negative sides, the oxygen. And the bonds are kind of canceling out the forces between them. Okay? Read in your book too. I feel like you're going to need that explanation to really understand this as well. Okay, let's take another example. Let's try. Okay, so this was an example. And we determined that this was not polar. Okay, because of rule 2. Because of the second rule. The bonds were, in fact, of equal strength, and they did pull in opposite directions. Okay, let's try another one. CCl4. After you figure out the Lewis structure, you will see that this is a tetrahedron. I forgot my H. So it would look something like this. The carbon is in the middle. We have the Cl pulling more strongly on that polar bond. So the arrow is pointing to the chlorine with its 6 other valence electrons. And we have another one coming down this way towards Cl. And we have one coming out toward us. And we have one going behind it. Okay, so there we have labeled our polar bonds on the molecule. So yes, the molecule does have polar bonds. The polar bonds cannot be of equal strength and pull in opposite directions. Are these bonds all of equal strength? Yes, they are, because they're all chlorine to carbon bonds. So they're all pulling that same strength. The chlorine is pulling at the same strength. Here is an example of a tetrahedron, this time made with grapes, okay? And you can kind of see how, again, there's no way that you could cut this molecule in half where you would see a positive side and a negative side, because any way you cut it, you have negative up here and you have negative on the bottom. The positive, the carbon, is kind of blocked off in the center. Okay, and that is because of rule 2. The polar bonds are all of equal strength and they're all pulling in opposite directions, so they're canceling each other out. So there's not a positive end and a negative end to this molecule. So this would not be polar either. Not polar. Okay, let's try another example. Erase. Okay, this time we're going to look at, I believe it was I'm using your examples from your book. This time it is Ascl3. Another example, Astatine, I believe that is. Trichloride, Ascl3. Okay, this time the As is in the center. It has 5 valence electrons. Let's check that. Is it in column 5? Yes, it is in column 5. So it has 5 valence electrons. So if you fill out the Lewis structures of these, you would see that it would have 3 covalent bonds with the 3 chlorines, and then it has 1 lone pair. So figuring out the Lewis structure first, then we can come up with the geometry. This geometry would be a pyramidal shape. Okay, we'll keep the lone pair at the top. So then we would have, I'm going to erase these electrons so I can draw my geometry a little bit better. So we would have 1 polar bond over here. Oh, let's see who is more electronegative. Astatine is in column 5. Chlorine is in column 7, so chlorine is going to be more electronegative. So we're going to draw our polar bonds pointing toward the chlorine. Then we have one coming out toward us. And then we have one bond going off behind to the third chlorine. Okay, so it would look like that. So it is pyramidal. Okay? Let me show you with my grapes and toothpicks. So instead of a tetrahedron here, we're based off of the tetrahedron shape, but we have one leg missing because we have a pair of valence electrons on one side of the astatine. So it would look like this, okay? Now the astatine is going to be more positive because the electrons are usually pulled toward the chlorines. So the chlorines, if we wanted to label their partial charges, like we've learned how to do, are all partially negative, and the astatine is partially positive. Is there a way that you could slice this molecule in half and show a positive side and a negative side? Yes, there is. You could slice it right through here. If I draw a line, it'd be kind of right through here, right? And then you'd have a positive side and a negative side. So this is a polar molecule. And looking at the rules, does it have polar bonds? Yes, it does. Do the polar bonds, are they of equal strength? Yes. But do they all pull in opposite directions? No, they're all pulling in this one kind of general direction, but there's nothing pulling up here, leaving this to be the more positive area and this to be the more negative area. So this is a polar molecule. Now we're going to add, okay, so it's a polar molecule. Some more notes about polar molecules. Polar covalent compounds. A compound is just a collection of the same type of molecule. Polar covalent compounds dissolve other polar covalent compounds. You will read about that in your book, why, for example, soap works, okay? And the reason for this is because they both have electrical charges. Okay, this molecule up here has an electrical charge because one part of it is positive and one part of it is negative. So it would be attracted to another compound or molecule that was also polar, that had a positive side and a negative side, because the positive and negative would be attracted to each other, and then the negative and the positive of the other would be attracted to each other. So polar covalent compounds dissolve other polar covalent compounds. And purely covalent compounds dissolve only other purely covalent compounds. I think my marker is about to die. So this is one practical way that knowing whether a molecule is polar or not polar is just used in everyday life. If you want to know if oil is going to dissolve in water, are they both would either have to be purely covalent compounds, or they both would either have to be polar covalent compounds. Now, you guys probably know that oil does not dissolve in water. So one of them is going to be purely covalent and one of them is going to be polar covalent. If you know the shape of water, H2O, it's bent, okay? The hydrogen is what has usually the positive charge, and this has the more negative charge, the oxygen. Would you be able to slice that molecule in half? So is it polar? Yes, you could. It does have a positive and a negative side. So water is an example of a polar compound, which means that oil must be not polar, which is purely covalent. So the two don't dissolve in each other. An easy way to say this is like dissolves like, meaning the two have to be alike. Polar and polar are alike, so they dissolve each other. Purely covalent and purely covalent are alike, so they dissolve each other. Okay, and that's a practical use of polar and purely covalent molecules. So that's the end of our notes from me for Module 9. If you, as you are continuing to work through, you need to look at the examples that go on to page 308 on your own. And if you need to add some more of your own notes into your notes, then do that, because that is helpful for the learning process to create your own notes as well. And we will handle questions with my students in class when I see you next.